All right, so the topic for this video is going to be parallelograms, and our essential question is going to be what are the properties of these parallelograms and how are problems solved with them. All right, so a little background information. We got our guy Euclid, father of geometry. It says Euclid began to focus his attention on quadrilaterals and the different properties of them. He started off with a parallelogram, and he eventually proved 4 key properties about them. So what is a parallelogram? A parallelogram is a quadrilateral with 2 sets of parallel sides. So oftentimes our parallelograms will look something like this. This will be generally how I draw them. And parallelograms just have these 2 sets of opposite sides being parallel. Remember, arrows on a diagram tell us that those sides are parallel. So example 1 says determine if the following quadrilaterals are parallelograms or not. Well, if we look at this first one, we can definitely see that these 2 sides are parallel. They've got the arrows, which means that we got to check if those other 2 sides are parallel. And how do we know if lines are parallel? Well, we look at the angle pairs. Remember, certain angle pairs are supposed to be congruent if lines are parallel, and certain angle pairs are supposed to be supplementary if lines are parallel. One set of angles that's supposed to be supplementary if lines are parallel are our consecutive interior angles here. And we can tell that 150 makes 150, not 180. So no, this is not a parallelogram because those consecutive interior angles or those same side interior angles, those things are not supplementary like they're supposed to be. However, on this next one, this 120 and this 60, that does make 180, which means that these 2 lines are parallel. So that's cool. And then at the same time, this 60 and this 120 does make 180, which means that these 2 lines are parallel. So we do have our 2 sets of parallel lines according to those consecutive interior angles or those same side interior angles, which means this is a parallelogram. And then lastly, we've got this rectangle, and same idea there, right? The 90 plus the 90 is 180. The 90 plus the 90 is 180. So we do end up, because of this 180, we got these 2 lines being parallel. And then because of this 180, we got these 2 lines being parallel, which means that, yeah, this rectangle is a parallelogram. Cool. Now, we mentioned up above that Euclid would eventually prove 4 key properties of these parallelograms, and we got those down here. The first key property is the parallelogram opposite sides theorem that says that if a quadrilateral is a parallelogram, then opposite sides are congruent. So those 2 sides have to be the same length. These 2 sides have to be the same length. Next up, we got the parallelogram consecutive angles theorem. It says if it's a parallelogram, then the consecutive angles, those angles that are next to each other, have to be supplementary. So that could look something like this. Maybe this is 80 and this is 100. That would be supplementary. And then going vertically, this 80 and this 100 would be supplementary. So every parallelogram should have consecutive angles that add up to 180 that are supplementary. Then we got the opposite angles theorem that says in every parallelogram, opposite angles like those 2 have to be congruent, and opposite angles like these 2 have to be congruent. Then we got the diagonals theorem, and that one says that if you've got a parallelogram, the diagonals, so the lines going from opposite vertex to opposite vertex, are going to bisect each other. They're going to cut each other into 2 equal parts. Okay, so let's dive into the backside here. For the rest of this thing, what we're going to be doing is we're going to try to prove why these things are. We're going to try to do exactly what Euclid did. And then we're also going to solve some problems, some algebraic problems. So this first one says prove the opposite angles theorem. So the opposite angles that we're going to look at in this one are angle D and angle B. We're going to try to prove why angle D must be congruent to angle B if ABCD is a parallelogram. So our given says that ABCD is a parallelogram. And we're going to try to start from there and prove why angle D and angle B have to be the same. So we start with our given, of course. And how are we going to do this? Well, my strategy is that by showing that diagonal AC, I've kind of split this parallelogram into two different triangles. And all the proofs that we've done previously in these previous videos have all involved congruent triangles. So here's my strategy. I'm going to try to prove that those two triangles have to be congruent, because if they're congruent, then I could use CP/CTC, corresponding parts of congruent triangles are congruent, to show that angle D must be congruent to angle B. So that's my strategy. Now, anytime you try to prove that two triangles are congruent, you need to gather three congruent things between them. So that's going to be my first step. I'm going to try to gather three congruent things between those two triangles. Then I'll be able to use CP/CTC to get the job done. Now, we don't have much to start with. We just have this parallelogram. Now, according to the definition of parallelogram, like we saw on the front page, we know that a parallelogram has two sets of parallel sides. So that means that AB must be parallel to DC, and AD has to be parallel to BC. Right? This has to be parallel to this, and this has to be parallel to this, according to definition of parallelogram. Okay, so we got some parallel sides. Now, those aren't any congruent things, though. But what I like about this is these two lines, they make some pretty cool alternate interior angles right there. So let's grab those. That would be angle DAC has to be congruent to angle BCA because of the alternate interior theorem. All right, alternate interior angles are always congruent if the lines are parallel, which we know since it's a parallelogram. And then at the same time, these parallel lines, make these alternate interior angles. So let's get those. Angle BAC has to be congruent to angle DCA because those are also alternate interior angles. Okay, so we got two congruent things. Now we need a third congruent thing, and that's just going to be the reflexive property in the middle. All right, both of those triangles share side AC, so we get AC congruent to AC, reflexive property. Okay, so I've got 1, 2, 3 congruent things between my two triangles, which means now I can go ahead and say that triangle, I'll say triangle ADC must be congruent to triangle. If I do ADC, I need to do CBA, and that's going to be by angle, side, angle. Right? If we follow our markings here, we have an angle, a side, and an angle. And now that those two triangles are congruent, that means that angle D must be congruent to angle B by CP/CTC. Now, if we had drawn in the diagonal going the other way, diagonal DB, we could repeat this proof and prove why angle A has to be congruent to angle C. That would work as well. But this kind of gets the job done. This shows why those opposite angles have to be congruent. That's what Euclid did back in the day. Okay, so we understand the logic behind why these parallelograms have these theorems at least. Now let's use them. Let's try to do some algebra here. So example 3 says solve for x and the measure of angle D. Okay, well, what do we know about those opposite angles in a parallelogram? Right, if this thing's a parallelogram, those opposite angles there have to be congruent, right? That's what we just proved. So we can just do 4x plus 20 is equal to 7x minus 40. If I subtract the 4x, I get 3x. Add the 40 over, I get 60 is equal to 3x. That means x has to be 20. And if we plug x back in, 4 times 20 is 80, plus 20 is 100. 7 times 20 is 140, minus 40 is 100. So I'm going to give myself a check. I checked my work there. It did show that those were the same. And then I'll say that the measure of angle D is equal to 100 degrees. Now for this one, it's equal to x and the measure of angle C. Now what do we know about these angles? These are not opposites, so they're not congruent, right? Angle A should be the same as angle C, but those consecutive angles, those same side interior angles, those are supposed to be supplementary. So 10x plus 10 plus 5x plus 20 has to be equal to 180. That'd be 15x plus 30 is equal to 180. If I subtract the 30, I get 15x is equal to 150. So x should be 10 here. Now if I plug that back in, for angle A, 10 times 10 is 100, plus 10 is 110. 5 times 10 is 50, plus 20 is 70. So that looks good to me because that does add up to be 180. Now they want us to find angle C, and angle C should be congruent to angle A, right? Because those are the opposites. So I will say that the measure of angle C is equal to 110. Cool, cool, cool. All right, so let's head back up for another proof and try to prove another one of those theorems that we saw in the front. This says prove the opposite sides theorem. So we've got ABCD being a parallelogram again, but this time we want to prove that AB is congruent to CD. So we want to try to prove that those opposite sides have to be the same. Now, conveniently, we can pretty much follow the exact same strategy. I'm still going to divide this thing up into two triangles, try to prove that the triangles are congruent, and then use CP/CTC to show that the sides are congruent. Okay, we've got our parallelogram. Okay, so first thing we know that if we're given a parallelogram, that means that we got some opposite sides being parallel. AB and DC are parallel. And AD is parallel to BC. These are also parallel. And that's because that's what the definition of a parallelogram says. Okay, so we got our parallel sides. Now let's start gathering our three congruent things. And I think we can honestly get away with just using the same sort of three things that we used on the last one. Since this is parallel to this, we can get these alternate interior angles. So that would be angle ABD is congruent to angle CDB. Alternate interior theorem. And then since these lines are parallel, we can get these alternate interior angles. So angle ADB has to be congruent to angle CBD, also by the alternate interior theorem. Okay, then we just need one more congruent thing. Let's grab the reflexive property in the middle. BD congruent to BD. Reflexive property. That gives us our 1, 2, 3 congruent things. And now that we've got our 3 congruent things, we can say that triangle ADB must be congruent to triangle CBD by angle side angle. Once again, it's angle side angle based on the markings there. And cool. Now we can just use CP/CTC. Since those two triangles are congruent, that means that all of their corresponding parts are also congruent. CP/CTC. Corresponding parts of congruent triangles are congruent. So that's why every parallelogram has opposite sides that are the same. Cool. Now, let's do a little bit more algebra. So we got two parallelograms down here. This first one, we're going to solve for x, y, and the perimeter. Well, what do we know about parallelograms? Well, opposite sides, like we just saw, must always be congruent. So let's start with x. 3x plus 1 must be equal to 7. Subtract the 1, we get 3x is equal to 6. That gives me x is equal to 2. If I plug that 2 back in, 3 times 2 is 6, plus 1 is 7. So, cool, that checks out. Our other set of opposite sides must also be congruent, so 3y minus 3 must be equal to 12. Add the 3 on over, get 3y is equal to 15. That means that y is 5. If I plug the 5 back in, 3 times 5 is 15, minus 3 is 12, so that checks out. That gets a check mark. And let's find the perimeter there. 7 plus 12 plus 7 plus 12. That's 19 plus 19, that is 38. So the perimeter, that's not how you spell perimeter. Perimeter must be 38. And then our last one here's got that diagonal thing going on here. Solve for x and y. Well, for x, I know that DE must be the same as EB. So let me do 8x plus 3 is equal to 10x minus 5. If I subtract the 8x, I get 2x minus 5. Add the 5 over, I get 8 is equal to 2x. So x is 4. Let me make sure that that works by plugging it back in real fast. If x is 4, then 8 times 4 is 32, plus 3 is 35. And then 10 times 4 is 40, minus 5 is 35. So got the same thing there. That diagonal was bisected, so that works. And then for the y, I'll need to do 3y minus 11 is equal to 22, because those two pieces, the diagonal, must also be the same since it got bisected. That's going to give me 3y is equal to 33 when I add the 11, so y is 11. Let me just plug that back in and check to make sure that that works also. 3 times 11 is 33, minus 11 is 22, which checks out with the other side being 22. So cool. All right, so hopefully you kind of understand the why behind these properties a little bit by doing those proofs, and you feel comfortable doing the algebra. For your turn for your practice here, you've got some basic ones to start off with just by doing some properties going on in here. And then you got to do a little solving in here as well. So give those a shot and then come back to the video when you are ready to check to see how you did. All right, so for the first one here, should have been pretty easy. If this is 60, x is 60, right? Opposite sides need to be the same, and y needs to be 40 since those need to be the same. For number 2, we got some angles in here. If angle B is 62, that should be the same as y, so y should be 62. And then for x, you had to do 180 minus 62 to get 118. So x should be 118. For number 3, we got a lot of things flying around in here. W, X, Y, and Z. Okay, where's W? Well, W is an alternate interior angle with this 30 down here. So I like W being 30. X is here. That should be the same as 5. That's the diagonal getting bisected. Y is another diagonal with the 3. And Z is an alternate interior angle with the 40. So 35, 3, and 40. This one says solve for x in the perimeter. Okay, well, I've got this set of opposite sides. I know that opposite sides need to be the same. So let's do 2x plus 6 is equal to 4x minus 8. Subtract the 2x, I get 2x minus 8 is equal to 8. Add the 8, we get 14 is equal to 2x, so x is 7. And then plugging that x back in, 2 times 7 is 14, plus 6 is 20. 4 times 7 is 28, minus 8 is 20, so that works. And inside DC, if we've got 7, that's 4 times 6, which is 42, minus 2 is 40, which means that's 40, which means that my perimeter, when I add up everything, should be 40, 40, 20, 20. That is 120. For this one, solve for x in the measure of angle A. Those are opposite angles there. Those should be the same. So I'll do 4x plus 10 is equal to x plus 85. That's 3x plus 10 is equal to 85. That's 3x is equal to 75. So x is 25. And if x is 25 and I plug this back in, both of these end up being 110, which is cool. That means I did that part right. But that means that angle A should be 180 minus 110 to get 70. The measure of angle A is 70, because remember, those consecutive angles need to be supplementary. Then lastly, this one says solve for x and dB. That 12 is just a complete distraction. If the diagonals are drawn in like this, we know that they bisect each other, so it should be the x plus 9 that is equal to the 5x minus 35. If I subtract the x, I get 4x. Adding the 35 over there is going to give me 44 is equal to 4x. So x ends up being 11. And if x is 11 and I plug it back in, then 11 plus 9 is 20. And 5 times 11 is 55, minus 35 is 20. So the whole thing there, the whole dB would be 40, right? dB is the entire diagonal, so dB is equal to 40. Okay, hopefully that went well for y'all, and that's going to wrap up this video.